All right, in this problem, we are going to calculate the design snow load for roof joists. So the question says the following data apply to the structure shown in the figure. The ground snow load is 20 psf, that's PG. The roof is fully exposed with wood shingles. We have open terrain, we have a risk category of 1, we have an unheated structure. The design code is ASCE 7-10, and the roof joists span from the exterior wall, which would be over here, to the ridge beam at the center of this gable roof. And the design snow load for the roof joists is most nearly A 10 psf, B 12 psf, C 16 psf, and D 20 psf. So this is a really great question for the PE because, or at least to practice on, because it requires us to go into our code, right? So as soon as we see this, we're thinking, okay, it's asking me about snow loads. It's telling me that the design code is ASCE 7-10. So let me open up ASCE 7 and go to chapter 7 for snow loads. And so there's really two things that we need to check here. The first one is going to be the sloped roof snow load, or PS. So the first thing that we are going to check is the sloped roof snow load PS. Okay, so what does PS equal? Well, we're going to go into ASCE 7, chapter 7, and we're going to scroll down until we find PS, right? So there's PG, that's what was given in the problem statement as 20 PSF. And if we keep going down, we'll find the sloped roof snow load PS. Okay, so PS is equal to CS times PF. And PF is the flat roof snow load, right? So we know that we're going to have to solve for PF. Okay, so we're going to go back up. And we saw PF earlier. And it's right over here, equation 7.3-1. So PF is equal to 0.7 times CE times CT times IS times PG. Okay, so we have the PG, the flat roof snow load, the ground snow load PG, but we need to find the other variables. So let's start with CE, okay? So we're going to go to table 7-2 to find CE, the exposure factor, CE. Okay, so this table tells us that if we want CE, we need to know both the exposure of the roof and the terrain category. So the terrain category could either be B, C, or D. And if we look at our problem statement, it tells us that this is open terrain. So we need to go to chapter 26 to figure out what the terrain category is. Remember, chapter 26 deals with wind loads. So if I go to chapter 26, okay, chapter 26. So I want to find the terrain category. So I'm going to go up here. And I find that chapter 26.7 gives me different surface roughnesses. And we see here open terrain, right? That's what we have, open terrain. So surface roughness C, all right? I'm going to write that down. We are surface roughness C. Okay, so I'm going to go back to table 7-2. And here we are. We have terrain category C. And then what is the exposure of the roof? Well, the problem statement says that the roof is fully exposed. So for terrain category C and a fully exposed roof, we know that CE is equal to 0.9. Okay, so let's write that down in our little scratch pad here. CE equals 0.9. Okay, the next item that we're going to solve for is CT. Okay, so we see right here, CT, the thermal factor, is provided for different levels of heating of the structure, right? And our problem statement says that we have an unheated structure. So an unheated and open air structure, we know that CT is equal to 1.2. So we'll write that down as well. Okay, IS, the next item that we need to solve for. So IS is the importance factor for snow, and the importance factors are given all the way back in chapter 1 for different structures. So if we go to chapter 1, we want to find the importance factor for snow load. Okay, right here. Importance factors by risk category of buildings and other structures for snow, ice, and earthquake loads, table 1.5-2. Okay, so based on our risk category, we can find the snow importance factor. And we are risk category 1. That's given right in the problem statement, risk category 1. So the snow importance factor, IS, is equal to 0.8. So we'll write that down as well. Okay, so now we can solve for PF, right? PF is equal to 0.7 times 0.9 times IS, our importance factor, 0.8 times PG, our ground snow load of 20 PSF. So we know that PF is equal to 12.1 PSF. Okay. So we also know that PS is equal to CS times PF, right? So we want to find that sloped roof snow load, PS, is equal to, well, what is CS? Well, we have to figure that out from figure 7-2. So if we go back to chapter 7, back to chapter 7. All right, so if we go to this figure here, we will find CS for different roof slopes. Okay, so we want to find out what CT is equal to. Well, earlier we said that CT is equal to 1.2. So we know that we need to use table 7-2C because it says cold roofs with C is equal to 1.2 or larger. Okay, so this figure provides two different lines. We have an unobstructed slippery surface indicated by the dashed line, and then all other surfaces use this solid line here. So the problem statement tells us that we have a roof fully exposed with wood shingles, right? So that is not a slippery surface. A wood shingle is a rough surface. So we're going to use this solid line, and then it gives us for various slopes. So for instance, we have a 6-on-12 slope. You use this solid line, 6-on-12, and you're at a CS of 1.0. So if we go back to here, we know that's PS is equal to 1.0 times our flat roof snow load of 12.1 PSF is equal to 12.1 PSF. Okay, so now we need to check unbalanced snow load. And for that, we're going to go to ASCE 7.6.1 for the unbalanced snow load. Okay, unbalanced snow loads for hip and gable roofs. So 7.6.1 says for hip and gable roofs with a slope exceeding 7-on-12 or with a slope less than 2.38 degrees, unbalanced snow loads are not required to be applied. So do we fall within that category? No, because our slope does not exceed 7-on-12. Our slope is 6-on-12. Okay. So for roofs with an eave to ridge distance W of 20 feet or less, having simply supported prismatic members spanning from ridge to eave, shall be designed to resist an unbalanced uniform snow load on the leeward side equal to I times PG. And that's exactly what we have, right? We have a eave to ridge distance of 19 feet, which fits right in that description there, 20 feet or less. And so we know that the uniform snow load on the leeward side has to be I times PG, okay? So our unbalanced snow load is equal to I times PG, and we already calculated our I is equal to 0.8 times PG of 20 PSF, and that's going to be equal to 16 PSF. And that is answer choice C, right? Because our 16 PSF controls. The 16 PSF is significantly greater than our 12 point PSF that we calculated earlier. So I think this was a really good sample PE problem because even though it's a relatively easy formula. It's basically plug and chug. You are required to leverage the code and go into various sections to find all of these different variables, right? So it's a good PE problem because you need to be familiar with ASCE 7 and know exactly where to find um, all of these different factors in order to calculate the design snow load. And with that, just wanted to say thank you very much for watching. And if you find these videos helpful, please like, comment, and subscribe.